Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The sands of Alexandria, once vibrant with the echoes of intellectual ferment, have yielded a name that resonates across millennia. Diophantus, his life, shrouded in a delightful obscurity, presents a challenge to historians. Precise dates, definitive biographical details, these remain frustratingly elusive. We are left, instead, with fragments, tantalizing glimpses through the lens of the Arithmetica. His seminal work, this circumstance, far from diminishing his stature, amplifies the mystique surrounding this pivotal figure. It compels us to focus not on the minutiae of his existence, but on the enduring power of his ideas. Reconstructing Diophantus's world is a task of piecing together scattered evidence. The very act of studying him becomes an exercise in the mathematical principles he himself pioneered a quest for solutions within the constraints of limited data. We know he flourished, likely in Alexandria, during the Hellenistic period, a time of extraordinary intellectual flourishing. Some scholars place him in the 3rd century, others in the 4th. The lack of certainty, however, does little to diminish the impact of his contributions. It is the Arithmetica that provides the clearest window into his genius. This collection of problems, meticulously solved, offers a profound insight into the development of algebraic thought. Before Diophantus, mathematical expression was often cumbersome, reliant on verbal descriptions and geometric constructions. The absence of a standardized symbolic language made the representation and manipulation of mathematical ideas unwieldy. Consider the challenge of expressing a simple equation like the unknown quantity plus 3 equals 7. Prior to Diophantus, this might have been written out in full, a laborious process, particularly when dealing with more complex relationships. The lack of a shared vocabulary hindered the efficient communication of mathematical concepts and limited the scope of exploration. The need for a more concise, flexible, and universally understood system was apparent. Diophantus, with characteristic ingenuity, addressed this challenge head-on. He is credited with introducing a system of notation that, while not identical to our modern algebra, represents a crucial step towards it. His innovations laid the groundwork for the symbolic language we use today. He introduced a symbol for the unknown, a crucial advance. He used the Greek letter S, likely representing the word arithmos number, to denote the unknown quantity. This was a significant departure from the purely rhetorical style of earlier mathematicians. The introduction of a symbol allowed mathematicians to manipulate unknown quantities directly, facilitating the formulation and solution of more complex problems. Furthermore, Diophantus developed symbols for powers of the unknown. He had a symbol for the square of the unknown, the cube of the unknown, and other powers. He also devised symbols for subtraction and equality. His notation, though not as fully developed as our current system, was a remarkable achievement for its time. It provided a framework for expressing mathematical relationships in a way that was far more compact and efficient than the methods previously employed. This enabled mathematicians to tackle problems that would have been nearly impossible to express, let alone solve, using earlier techniques. The impact of Diophantus's symbolic notation cannot be overstated. It facilitated the development of algebraic techniques and paved the way for the exploration of more abstract mathematical concepts. The ability to represent unknowns and perform operations symbolically allowed mathematicians to move beyond specific numerical examples and to formulate general solutions. This shift from concrete to abstract thinking was a pivotal moment in the history of mathematics. It marked the beginning of a new era of mathematical discovery. The evolution of algebraic notation is a testament to the enduring influence of Diophantus. His work, though initially limited by the constraints of his time, set a precedent for the development of a more sophisticated and comprehensive symbolic language. While his notation differed from the standardized system we use today, it was a crucial step in the right direction. The symbols he introduced, the concepts he pioneered, these provided the foundation upon which later mathematicians, from the Islamic Golden Age to the European Renaissance, built their own systems. Consider the subsequent contributions of figures like Al-Khwarizmi, whose work on algebra, derived from the Arabic word algebra, further refined and expanded upon Diophantus's ideas. Al-Khwarizmi, while building upon the foundations laid by the Greeks and Indians, played a crucial role in systematizing algebraic methods and introducing new techniques for solving equations. The impact of Diophantus's work, even if indirectly, is evident. The ability to represent unknowns and perform operations symbolically, as Diophantus first demonstrated, was essential for the development of these advancements. The influence of Diophantus extended beyond specific symbols. His approach to problem solving, his emphasis on general methods, and his systematic exploration of algebraic relationships all contributed to the development of a more rigorous and abstract mathematical framework. He demonstrated the power of using symbols to represent relationships between quantities, a concept that would become central to the development of modern algebra. The legacy of Diophantus is evident in every algebraic equation we encounter, in every mathematical problem we solve. His contribution to the development of algebraic notation, though sometimes overlooked, is fundamental. His work established the groundwork for the symbolic language that underpins modern mathematics and science. The very act of manipulating equations, of solving for unknowns, is a direct descendant of the system he pioneered. It is a system that allows us to explore the world through the lens of mathematical relationships, to uncover the hidden structures that shape our universe. His influence is a constant presence, a subtle reminder of the enduring power of human intellect. The Arithmetica, Diophantus's magnum opus, stands as a landmark in the history of mathematics, a testament to his ingenuity and a cornerstone of algebraic thought. The work, a collection of problems and their solutions, is far more than a mere compendium of mathematical puzzles. It represents a significant shift in mathematical methodology, a move toward the systematic exploration of relationships between numbers. The Arithmetica is not merely a series of solved problems, it is a demonstration of a new way to approach mathematical inquiry. The structure of the Arithmetica is itself noteworthy. It is organized around specific types of problems, each explored with a consistent methodology. This organization, rather than a random assortment of mathematical curiosities, reveals a conscious effort to categorize and classify mathematical challenges. Diophantus grouped problems according to the nature of the equations involved and the types of solutions sought. This systematic approach is a departure from earlier mathematical texts, which often presented isolated examples or solutions without a clear framework. This framework facilitated the development of generalized methods applicable to a range of similar problems. At the heart of Diophantus's work lies his fascination with indeterminate equations, where the number of unknowns exceeds the number of equations. These equations, which have an infinite number of solutions, presented a unique challenge. The task was to find rational solutions expressed as ratios of integers. This focus on rational solutions distinguishes Diophantus's work from the geometry-focused mathematics of his predecessors. He wasn't primarily concerned with geometric constructions or proofs. His focus was on the numerical solutions themselves. The types of problems Diophantus addressed were varied and ingenious. He explored linear equations, quadratic equations, and even equations involving higher powers. The Arithmetica contains problems involving finding integer solutions to equations, determining the sides of right triangles, and dividing numbers into specific ratios. Each problem presented a unique set of challenges, demanding innovative strategies for solution. The variety of problem types demonstrates Diophantus's broad understanding of mathematical relationships, showcasing the flexibility of his approach. One of the significant innovations of the Arithmetica is its treatment of problems with multiple unknowns. Diophantus developed methods to systematically eliminate or transform equations, reducing complex problems to simpler forms that could be solved. He employed clever substitutions and manipulations to isolate variables and find solutions. The techniques he employed are a direct precursor to the algebraic methods we use today. His methods, though sometimes cumbersome by modern standards, represent a significant advance in the art of problem solving. The challenges of solving these types of equations in Diophantus's time were considerable. The lack of standardized notation, the absence of developed algebraic techniques, and the absence of a well-defined framework for dealing with indeterminate equations all presented obstacles. Diophantus, however, overcame these obstacles with remarkable ingenuity. He developed his own notation, devised clever substitutions, and employed insightful reasoning to arrive at solutions. His work represents a triumph of mathematical creativity, a testament to his ability to think outside the constraints of his time. The impact of the Arithmetica on subsequent mathematicians has been profound. It served as a source of inspiration and a guide for centuries. Mathematicians, both in the ancient world and during the Renaissance, studied the Arithmetica and drew inspiration from its methods. The work influenced the development of algebra, number theory, and other branches of mathematics. The systematic approach to problem solving, the focus on indeterminate equations, and the development of algebraic techniques all had a lasting impact on the evolution of mathematical thought. The Arithmetica also helped to shape the way mathematicians approached problem solving. Diophantus's work emphasized the importance of finding general methods for solving problems rather than relying on ad hoc solutions. This emphasis on generality laid the groundwork for the development of abstract algebra and the formalization of mathematical concepts. His focus on systematic approaches helped to transform mathematics from a collection of isolated techniques into a coherent and unified discipline. The influence of the Arithmetica is also evident in the development of algebraic notation. Diophantus's use of symbols to represent unknowns and operations, though not as fully developed as modern notation, paved the way for the symbolic language of algebra. His work demonstrated the power of using symbols to simplify mathematical expressions and to represent relationships between quantities. This development, in turn, facilitated the development of more powerful methods for solving equations and exploring mathematical concepts. The Arithmetica is more than a collection of solved problems. It is a testament to the power of human intellect, a demonstration of how creative thinking can overcome seemingly insurmountable challenges. The work represents a significant step forward in the development of mathematics, a move toward a more systematic and abstract approach to problem solving. The legacy of Diophantus is evident in every algebraic equation we encounter, in every mathematical problem we solve. His contribution to the development of algebraic notation, though sometimes overlooked, is fundamental. His work established the groundwork for the symbolic language that underpins modern mathematics and science. The very act of manipulating equations, of solving for unknowns, is a direct descendant of the system he pioneered. It is a system that allows us to explore the world through the lens of mathematical relationships, to uncover the hidden structures that shape our universe. His influence is a constant presence, a subtle reminder of the enduring power of human intellect. The Arithmetica is a landmark achievement, a testament to the enduring power of mathematical thought. Having established the foundational principles of Diophantus's work, we now turn to examine specific instances of his problem-solving techniques, as they are illustrated within the Arithmetica. These examples provide concrete insights into his innovative methods, showcasing the ingenuity and the challenges inherent in his approach. His solutions, while at times cumbersome by modern standards, reveal a brilliant mind grappling with problems that continue to resonate with mathematicians today. Consider, for example, problem 8 from book 4.2. The objective is to divide a given square number into two other square numbers. Diophantus presents a specific case to express the number 16 as the sum of two squares. He begins by proposing that one of the squares be of the form, a certain number of units subtracted from a certain number of units. That is, if we let one square be represented as, and I will speak it out, 1x minus 2, the whole quantity squared. Now, to find the second square, he subtracts 1x minus 2, the whole quantity squared from 16. Expanding 1x minus 2, the whole quantity squared yields 1x squared minus 4x plus 4. Subtracting this from 16 results in 12 plus 4x minus 1x squared. Diophantus then sets this expression equal to another square, specifically 4 squared, which is 16. This approach, while seemingly circuitous at first glance, reveals Diophantus's strategy. He has cleverly converted the problem into a single unknown, allowing him to manipulate the equation more effectively. The equation 12 plus 4x minus 1x squared equals 16 can then be simplified using the principles of algebra to isolate x. The goal is to find a value for x that makes 12 plus 4x minus 1x squared a perfect square. The solution proceeds by recognizing that since 1x minus 2, the whole quantity squared, is a square, its value must be less than 16. The problem then becomes finding a value for x that satisfies this condition. By carefully choosing the initial expression, Diophantus has created a system where the solution can be found through a combination of algebraic manipulation and insightful observation. The method he employs to find a suitable value for x is a testament to his ingenuity. He does so by choosing a rational number that, when substituted into the equations, yields the correct answer. The specific value of x that satisfies the equation is dependent on the initial assumption that one of the squares is 1x minus 2, the whole quantity squared. This substitution allowed him to determine the sides of the two squares that sum to 16. The ultimate solution is expressed in terms of fractions, demonstrating his willingness to embrace rational numbers as valid solutions, a characteristic of his more general approach to problem solving. This particular example highlights a fundamental aspect of Diophantus's methodology, the reduction of a problem to a manageable form through the introduction of unknowns and the manipulation of algebraic expressions. It reveals his ability to see beyond the surface, to identify underlying relationships between numbers and equations. The problem is not simply a matter of finding two squares, it is a demonstration of a systematic approach to solving indeterminate equations. Another illustrative example, problem 10 from book 4.2, presents a similar challenge to express a given number, in this case, a number that is not a perfect square, as the sum of two squares. The number in question is 13. Diophantus's approach is again ingenious. He sets one of the squares as 1x squared, The second square is then expressed as 13 minus 1x squared. This is then set equal to 2x minus 3, the whole quantity squared. Expanding 2x minus 3, the whole quantity squared yields 4x squared minus 12x plus 9. The equation becomes 13 minus 1x squared equals 4x squared minus 12x plus 9. This equation is then simplified to solve for x. The solution involves a series of algebraic manipulations, including combining like terms and isolating x. The resulting value for x is a fraction. Substituting this value back into the original expressions yields the sides of the two squares that sum to 13. The solution provides the two squares, with each side expressed as a fraction. This method, while different in its specific details from the previous example, shares the same underlying principle of strategic introduction of unknowns and manipulation of algebraic expressions to reduce a complex problem to a solvable form. It showcases Diophantus' ability to transform a seemingly intractable problem into one that can be addressed with a combination of algebraic skill and insightful observation. The significance of these techniques extends beyond the mere solutions to specific problems. They demonstrate the power of algebraic thinking, the ability to represent unknown quantities with symbols and to manipulate equations to uncover hidden relationships. These methods are precursors to the development of modern algebra, laying the groundwork for the symbolic language that would later revolutionize mathematics. The challenges Diophantus faced in solving these problems are also noteworthy. He worked without the benefit of modern algebraic notation, relying instead on a cumbersome system of verbal descriptions and abbreviations. His solutions are often expressed in terms of rational numbers, showcasing his willingness to embrace fractions as valid solutions. This willingness is a testament to his understanding of the underlying mathematical principles. The significance of Diophantus' work lies not only in the specific solutions he provides, but also in the innovative methods he employed. He pioneered a systematic approach to solving algebraic problems, introducing unknowns, manipulating equations, and seeking solutions that satisfy the given conditions. His methods represent a significant step forward in the development of mathematics, a move toward a more abstract and systematic approach to problem solving. The problems Diophantus tackled, while sometimes appearing elementary by our standards, represent a profound shift in mathematical thinking. He moved beyond the purely geometric approach of earlier mathematicians, embracing a more abstract and symbolic language. This shift allowed him to explore a wider range of problems and to develop more general methods for solving them. The problems he presented and the solutions he devised demonstrate a deep understanding of number theory and algebra. He was, in essence, exploring the fundamental relationships between numbers, laying the groundwork for future generations of mathematicians. His influence, though often subtle, is pervasive in every algebraic equation we encounter, in every mathematical problem we solve. The rediscovery and subsequent translation of Diophantus' Arithmetica was a pivotal moment in the history of mathematics. The manuscript, preserved through centuries of intellectual shifts, re-emerged into the European academic landscape, carrying with it a potent seed of abstract thought. This reintroduction, occurring primarily during the Renaissance and the subsequent centuries, sparked a renewed interest in algebra and number theory. The impact was not immediate, nor was it uniform across Europe. Rather, it was a gradual process of assimilation and adaptation, with Diophantus' ideas subtly, yet profoundly, altering the course of mathematical inquiry. The Arithmetica in its translated form provided a powerful set of tools and, perhaps more importantly, a novel approach to problem solving that would influence generations of mathematicians. One of the primary challenges faced by early interpreters involved understanding Diophantus' methods. His use of syncopated algebra, while a significant advance over the rhetorical algebra of the Greeks, presented its own hurdles. The absence of a fully developed symbolic notation, combined with the inherent ambiguities of translated texts, required scholars to engage in a painstaking process of reconstruction. They had to decipher the meanings of his abbreviated terms and the nuances of his problem-solving techniques. This process, however, was itself a catalyst for progress. The very act of grappling with Diophantus' work forced mathematicians to confront the limitations of their own understanding and to seek more precise and efficient ways of expressing mathematical ideas. This struggle, in essence, fostered innovation. The influence of Diophantus is particularly evident in the work of Pierre de Fermat. Fermat, a lawyer by profession, possessed a keen interest in mathematics, and he meticulously studied the Arithmetica. He not only absorbed Diophantus' methods, but also extended them, posing new problems and devising new solutions. Fermat's marginal notes, scribbled in his personal copy of the Arithmetica, are legendary. These notes, often cryptic, contain statements of theorems that Fermat claimed to have proven, although he frequently omitted the proofs themselves. His most famous claim, the so-called Fermat's last theorem, is a direct descendant of Diophantine problems, a testament to the enduring power of Diophantus' ideas. Fermat's fascination with number theory, his focus on integer solutions, and his innovative use of mathematical reasoning all bear the indelible mark of Diophantus. Beyond Fermat, the influence of Diophantus can be observed in the development of algebraic notation itself. While Diophantus' notation was rudimentary compared to the symbolic language we use today, it represented a crucial step toward abstraction. His use of symbols for unknowns and operations, though not fully developed, provided a foundation upon which later mathematicians would build. The evolution of algebraic notation, from the syncopated algebra of Diophantus to the fully symbolic algebra of Viet and Descartes, was a gradual process of refinement and elaboration. Each generation of mathematicians, building upon the work of their predecessors, gradually refined the symbolic language, making it more concise, more powerful, and more adaptable to a wider range of problems. Diophantus, therefore, served as a crucial link in the chain of mathematical progress. The impact of Diophantus extended beyond the realm of pure mathematics. His work influenced the development of other scientific disciplines, particularly those that relied on mathematical modeling. The methods he developed for solving algebraic equations and for exploring the relationships between numbers provided a valuable toolkit for scientists and engineers. The ability to formulate and solve mathematical models became increasingly important in fields such as physics, astronomy, and engineering. Diophantus' legacy, therefore, resonates throughout the history of science. Furthermore, the challenges of interpreting ancient texts, such as the Arithmetica, have shaped our understanding of the history of mathematics. The process of translation, annotation, and interpretation requires careful attention to detail and a deep understanding of the historical context. Scholars must consider the cultural and intellectual climate in which the text was written, the author's intentions, and the limitations of the available evidence. This work of historical reconstruction is, in itself, a valuable endeavor. It forces us to confront the complexities of the past and to appreciate the intellectual achievements of previous generations. The modern relevance of Diophantus' contributions lies in his enduring impact on mathematical inquiry, his focus on abstract problem solving, his development of algebraic methods, and his exploration of number theory continue to inspire mathematicians today. The problems he posed and the solutions he devised serve as a reminder of the power of mathematical reasoning and the importance of seeking general solutions. His work is a testament to the enduring value of abstract thought and its capacity to illuminate the world around us. The historical context surrounding Diophantus' work offers valuable insights into the evolution of mathematical thought. His influence on later mathematicians, particularly Fermat, highlights the importance of intellectual exchange and the gradual accumulation of knowledge. The challenges of interpreting his methods and the development of algebraic notation underscore the inherent difficulties in understanding the past. The enduring relevance of his contributions to mathematical inquiry demonstrates the lasting impact of his ideas. Diophantus, in essence, represents a pivotal moment in the history of mathematics, a bridge between the ancient and the modern. His work continues to challenge and inspire, reminding us of the power of human intellect and the enduring quest for knowledge. The echoes of Diophantus' intellectual legacy resonate still, a testament to the enduring power of abstract reasoning. His influence, traversing the centuries, extends far beyond the confines of pure mathematics. His work, a cornerstone in the development of algebraic thought, provided a foundation upon which subsequent generations of mathematicians constructed their own edifice of knowledge. The very nature of his problems, demanding general solutions rather than specific numerical answers, fostered a shift in perspective, moving away from concrete calculations toward the realm of symbolic manipulation in abstract relationships. This transition, subtle yet profound, helped shape the trajectory of mathematics, enabling the exploration of increasingly complex concepts and the articulation of universal principles. Consider the enduring fascination with Diophantine equations themselves. These problems, deceptively simple in their formulation, frequently conceal profound complexities. They continue to captivate mathematicians, posing challenges that demand ingenuity and persistence. Contemporary researchers still grapple with these equations, seeking to unravel their mysteries and to find new methods of solution. The study of Diophantine equations has led to significant advancements in number theory, cryptography, and computer science, demonstrating the surprising applicability of abstract mathematical concepts to real-world problems. The very act of attempting to solve these equations, the struggle to find general solutions, embodies the spirit of mathematical inquiry, a relentless pursuit of understanding. Furthermore, the impact of Diophantus' work extends into the realm of pedagogy. His emphasis on problem-solving, on the active engagement with mathematical ideas, continues to inform modern teaching methodologies. The Diophantine problems, with their inherent elegance and their capacity to stimulate curiosity, provide a valuable tool for educators. They encourage students to think critically, to develop their problem-solving skills, and to appreciate the beauty and power of mathematical reasoning. The enduring appeal of these problems underscores the importance of fostering a spirit of inquiry, of encouraging students to embrace the challenge of intellectual exploration. The challenges inherent in understanding Diophantus' work offer a valuable perspective on the history of mathematics. The absence of a standardized algebraic notation, the reliance on rhetorical methods, presents obstacles to modern readers. These difficulties, however, also offer a unique opportunity to appreciate the intellectual ingenuity of the ancient Greeks, to recognize the remarkable achievements of a civilization operating with a limited set of tools. The process of deciphering Diophantus' methods, of reconstructing his thought processes, provides a powerful reminder of the evolution of mathematical notation and the gradual refinement of mathematical techniques. The difficulties, in essence, highlight the remarkable nature of the accomplishment. Moreover, the influence of Diophantus on subsequent mathematicians, particularly Pierre de Fermat, underscores the importance of intellectual exchange. Fermat, chiefly inspired by Diophantus' Arithmetica, built upon the foundations laid by his predecessor. He not only studied the problems posed by Diophantus, but also sought to extend their scope, to generalize their solutions, and to develop new methods of analysis. Fermat's marginal notes, scribbled in his copy of the Arithmetica, became the seeds of new mathematical discoveries, leading to the development of number theory and the formulation of fundamental theorems. The interaction between these two mathematicians, separated by centuries, highlights the collaborative nature of mathematical progress, the way in which ideas were transmitted, refined, and built upon over time. The significance of Diophantus' contributions reaches beyond the specific problems he addressed or the particular methods he employed. His work embodies a fundamental shift in mathematical thinking, a move toward abstraction and generalization. This shift paved the way for the development of modern algebra, calculus, and other branches of mathematics. Diophantus, in this sense, is a pivotal figure, a harbinger of a new era in mathematical thought. The legacy of his work is not solely confined to the specific solutions he provided, but in the very essence of his approach, the spirit of inquiry that continues to inspire mathematicians today. The enduring relevance of Diophantus' contributions stems from their ability to illuminate the fundamental principles of mathematics. His focus on finding general solutions, on expressing relationships in terms of variables, laid the groundwork for the development of algebraic methods. The problems he posed, the techniques he employed, helped to establish a framework for the analysis of mathematical structures. The enduring impact of his work underscores the importance of abstract thought and its capacity to illuminate the world around us. Mathematical reasoning, as exemplified by Diophantus, is a powerful tool for understanding the universe, for uncovering the hidden patterns that govern its behavior. The difficulties encountered in interpreting Diophantus' work, the challenges of understanding his methods, serve as a reminder of the evolution of mathematical thought. The development of algebraic notation, the gradual refinement of mathematical techniques, represents a continuous process of improvement. The very act of grappling with Diophantus' problems, of attempting to understand his solutions, allows us to appreciate the progress that has been made. The evolution of mathematics, like the evolution of any field of human endeavor, is a story of incremental advancements, of the gradual accumulation of knowledge. In conclusion, Diophantus of Alexandria stands as a giant in the history of mathematics, a pioneer whose contributions continue to resonate today. His work, a testament to the power of abstract thought, shaped the course of mathematical development. The enduring relevance of his problems, the influence of his methods, and the profound impact of his work on subsequent mathematicians all underscore his significance. Diophantus did more than solve problems. He helped to establish a new way of thinking about mathematics, a way that continues to inspire and challenge us. His legacy is not simply a collection of solutions, but a spirit of inquiry, a commitment to the pursuit of knowledge, a recognition of the power of human intellect to illuminate the world. His work is a beacon, guiding us toward a deeper understanding of the universe and the enduring beauty of mathematical truth. His name, synonymous with the very essence of algebraic thought, will forever be etched in the annals of mathematical history.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.